Hello everyone, this is the presentation video for the CVPR 2023 highlight paper, Frequency-Modulated Point Cloud Rendering with Easy Editing. I'm the co-first author of this paper, Xiaoyang Huang. This paper presents a point cloud rendering pipeline for novel view synthesis, which enables high-fidelity detail reconstruction, real-time rendering, and user-friendly editing. In contrast to implicit rendering, our pipeline supports high-fidelity interactive editing based on point cloud manipulation. In the heart of our pipeline is an adaptive frequency modulation module called Adaptive Frequency-Net or AFNet, which uses a hypernetwork to learn the local texture frequency to modulate the implicit radiance signal at a small computational budget. At the beginning, we would like to explain the motivation of this work. First, why do we focus on point clouds rendering? Point clouds provide explicit geometry, which brings two main advantages. It enables single sampling and benefit acceleration. Also, point clouds are ideal for interactive editing. Second, why do we use frequency modulation? The texture frequencies of a CD scene are region-dependent. For example, the back of the chair has a smooth texture, where the cushion texture changes rapidly between yellow and green. We believe that the weak texture and strong texture regions should be processed by neural networks adaptively. To this end, we propose AFNet, which introduces frequency modulation into radiance mapping. First, we encode texture frequency omega and phi from the query coordinate x. Here, omega and phi denotes the frequency and phase of a sinusoidal signal respectively, and x is a spatial point in a 3D scene. The encoding network is implemented as an MLP, which is composed of two linear layers and a ReLU layer in between. Since its output is injected into the main network consecutively, we call it hypernetwork. In step 2, we inject the predictive frequency and phase into the input feature using a sine function, and then multiply the sine function with the original input feature element-wise. We name this operation as adaptive frequency layer, or in short, AF layer. Somehow it replaces the activation layer in the MLP. Theoretically, in the chair scene, we wish that the back of the chair would correspond to a high frequency, while the cushion would correspond to a low frequency. Finally, our proposed AFNet is composed of a hypernetwork that predicts frequency information and a stack of AF layers and linear layers. The output dimension of the AFNet is RGB plus additional feature for 2D refinement. Next, we demonstrate the whole pipeline of our method, which is built upon one of our previous works. Our pipeline is consisted of 3 steps. First, for each ray, we estimate its interaction point against the object surface using the coordinate rectification technique proposed in this previous work. Then we feed the estimated surface point into our proposed AFNet. Since the AFNet maps each surface coordinates to RGB, an additional feature, the output of all rays would form a 2D raw image and a 2D feature map, which is fed into a UNet to predict its RGB offset. The raw image is combined with the offset to form the final RGB image. Finally, we demonstrate how our method could be used in user editing. At object level, when user determine the transformation in an interactive interface, such as MeshLab, and render the new scenes, we simply map the transformed coordinates back into the original space and invert feature using the AFNet. This method could render realistic image for object-level editing, such as object translation, scaling, and rotation. For scene-level composition, we render each scene respectively to obtain an RGB image for each scene and generate a mask by comparing the G buffer for each pixel. Then we combine the images together using the generated mask. This method can combine different scenes without the need of cross-scene chaining. We conduct experiments on various datasets, including NeRF-Synthetic, Tengs and Temples, ScanNet, and DTU. We compare our method with prior art on several perspectives: model size, rendering speed, editing ability, and image quality. Overall, our method achieves high rendering quality and flexible editing with a small model size while rendering in real time. Here, we compare the image details of different methods. Our method achieves notable fidelity in most regions, whether it has a strong or weak texture, such as the metal bore and the translucent drum. And this is our result on Tengs and Temples. Our method preserves high fidelity detail compared to other methods. This is our editing demos in object level, in which we duplicate, rotate, and rescale the target object in a 3D scene and render them into images. Our method could achieve realistic rendering results after editing. This is the demos for scene composition. We combine the scene in NeRF-Synthetic and render the new scenes in surrounding views. In conclusion, we could develop a novel point cloud rendering pipeline which enables high-fidelity reconstruction, real-time rendering, and user-friendly editing. Experiments on major benchmarks demonstrate the proposed methods outperforms existing point cloud rendering methods and achieve the state-of-the-art. If you are interested in our work, please check out the code on GitHub. Thanks for listening.